This lesson talks about definite integration, where you have to do a u substitution, kind of like we did with indefinite integration, in order to get things going on. This is actually a much easier way to do a definite integral than you might think. So, first example, if I do the integral from -2 to 1 of 3x squared plus 4 quantity cubed times x, and then times dx. Looking at this from a perspective of an indefinite integral, I can see that I have this kind of random x sitting out there by itself. And if I let u be equal to 3x squared plus 4, which is the thing that's being cubed, then du would have to be 6x times dx. So dx is equal to 1 over 6x. Now, when I do the replacements, and this is key here, I have to do them in several places. So not only do I take this and I substitute it with u, and I take the dx and substitute that, I must also account for the 1 and the 2. These, as you remember, were called the limits of integration. And in essence, those are x values. This is from -2 to 1 on x, but I want to change it so that it's on u. So I actually need to use this as a function of u. This is actually kind of like u of x is equal to. So when I make the changes and convert everything, I'm essentially converting everything to u's, and I'm never looking back. So 3x squared plus 4 gets replaced with u, times I have that x, times dx is 1 over 6x. Sorry, 1 over 6x du. I got the du there. And then my -2, I'm going to go u of -2 is equal to 3 times -2 squared plus 4. 3 times -2 squared plus 4 is 12. 4 times 3, 12, 16. And then I go u of 1, which is equal to 3 times 1 squared plus 4, or 7. So my limits now become 16 to 7. If I clean this up, cancel the x's out, take out a 1/6, I get 1/6 of the integral from 16 to 7 of u cubed du. And if I integrate that, that is 1/6 u to the 4th over 4 from 16 to 7.
I'll be gone.
So then you do 1/6. 7 to the 4th is 2401. 16 to the 4th is the same as 2 to the 4th to the 4th, which is 65536. And anyway, that simplifies down to negative 63135 over 24. Okay. Number 2. Integral from 0 to 1 of r times the square root of 1 minus r squared dr. We would let u be equal to 1 minus r squared, which means du is equal to -2r dr. So dr is equal to du over -2r. Then I'm going to do the substitutions. So let's kind of try to do this in one little swoop. My r's cancel. I'm going to factor a -1/2 out. I get the integrals. I'm not going to put 0 and 1. I'm going to take 0 and plug it in here, which gives me 1 minus 0 squared, so that gives me a 1. And then if I plug 1 in, I get 0. So it looks like I just switched the limits, but I didn't. I actually did u of 1 is equal to 0, and u of 0 is equal to 1. Then that gives me the square root of u, which is another way of saying u to the 1/2 du. So this changed everything. Now you'll notice how this is negative, and the limits effectively were switched. So I'm actually going to rewrite it as 1/2 the integral from 0 to 1 of u to the 1/2 du, making the sign positive and switching the limits. So now we integrate 1/2 times, this is 2/3 times u to the 3/2 from 0 to 1. 2/3 times 1/2 is 1/3, and I get 1/3. and this just gives me 1 minus 0. So my integral is just 1/3. Note how we never change things back from u's once we convert to u's. Okay, number 3, integral from pi over 6 to pi over 4 of sine of 2 theta d theta. This is a case of where some of you were saying we don't quite need to do u substitution. I'm going to do it anyway to show how the limit change makes this a lot easier. So if u is 2 theta, du is equal to 2 d theta, or d theta is equal to 1/2 du. So in my integral where I change over to u's, my 1/2 gets pulled out. My limits of integration become pi over 3 to pi over 2, 2 times theta. And this is just the sine of u du. And then I can go ahead and integrate this. It's going to be 1/2 times, the integral of sine is negative cosine of u. And that's going to be from pi over 3 to pi over 2. If I pull the negative out, make it negative 1/2, and then I go cosine of pi over 2 minus the cosine of pi over 3. So I get negative 1/2, cosine of pi over 2 is 0, cosine of pi over 3 is 1/2, negative 1/2 times negative 1/2, and I get 1/4. Okay, number 4, I'm going to star this one because it's a little bit more complicated than the ones we've done so far. We're going to do this as an indefinite integral, just get practice with this again, but my indefinite integral of sine squared x dx. If I think about it, there's no good thing to let u be equal to, and this isn't really going to work well unless I do a trig substitution. So when I see sine squared, remember we can replace that with something, so you guys need to know that the sine of 2 theta is equal to 2 sine theta cosine theta, that the cosine of 2 theta is equal to one of 3 things. You can do cosine squared minus sine squared, you can do 2 cosine squared minus 1, or you can do 1 minus 2 sine squared theta. And it's that last one we're going to want to do. So I'm going to take that last identity and solve it for sine squared. If I do, I get sine squared theta is equal to 1 minus cosine of 2 theta over 2. That's a quick way to derive the sine squared identity without having to memorize it. So this whole thing now just gets substituted. The integral of sine squared x becomes the integral of, if I split that up, becomes 1/2 minus 1/2 cosine of 2x dx. A couple ways I can deal with that, but I actually can factor a 1/2 out. Just leave that as 1 minus the cosine of 2x dx. It's an easy way to think about it. If I let u equal 2x, du is equal to 2 dx. So dx is equal to 1/2 du. Then I keep the 1/2 factored out and have the integral of, that'd be 1 minus, and this is the cosine of u, and then that 1/2 would be kind of just sitting right here out in front of that part, and du. And the integral of 1 doesn't really affect it that much, because the integral of 1, it's technically the integral of 1 dx, and dx is kind of did the du thing a little bit separately, so that's okay. So I have 1/2. Actually, I should split it up. I'm going to do this more correctly now. So let's take one step and split this into the integral of 1 dx minus, I'm going to distribute the 1/2 and do the integral of, I'm just going to do u with the cosine. So it's going to be the integral of 1/2 cosine of u du. That way I can really make this part be x. This part gets pulled out as minus 1/4 sine of u, which is the sine of 2x, then plus c because it's an indefinite integral. And see, that plus c really can kind of just be off to the side and account for both indefinite integrals because they each had separate c values, and if I just add up different c values, I get another c value. So this is acceptable, and I get x over 2 minus sine of 2x over 4 plus a constant. Okay, number 5. The integral from 0 to 2 of x over the square root of 1 plus 2x squared dx. So if I do this, I say u is equal to 1 plus 2x squared, which means du is the same as 4x dx, or dx is equal to du over 4x, which means that the x's cancel. I'm going to factor out a 1/4. I'm going to change my limits. 0 plugs in and becomes 1. 2 plugs in and becomes 9. And I get 1 over root u, which is the same as u to the negative 1/2 du. So you can see how in very quick steps you make complicated integrals become really simple. And if I integrate the u part, I get u to the 1/2 times 2. So this is times 2 times u to the 1/2 from 1 to 9. So this just becomes 1/2 times 3 minus 1, or 1. Number 6, I can do the integral of x squared, 2 minus x dx. This is an indefinite integral, so typically I would let u equal the 2 minus x, and du is equal to negative 1, or just negative dx. And if I still have this x squared, that means I need to take this piece and convert that. So x is equal to 2 minus u. So x squared is equal to u squared minus 4u plus 4. I'm going to go ahead and do all these substitutions. So x squared is u squared minus 4u plus 4. This is times root u. There's a negative that I'm going to stick out in front for the du equals dx, and I get du.
Hey, so wait, or Mr. Elliott. So this.
So when I multiply this out, I get u to the 5/2 minus 4u to the 3/2 plus 4u to the 1/2 du. And then if I integrate, I get 2u to the 7/2 over 7 minus 4. So there's a 4 already there, so 4 times, this would be 2u to the 5/2 over 5, then plus 4 times 3u, or sorry, 2u to the 3/2 over 3, and then just a plus c off to the side. So not an easy one to write, but remember u is 2 minus x, so I could go negative 2 times 2 minus x to the 7/2 over 7. This would be plus 4. This would be 8. 2 minus x to the 5/2 over 5 minus, this would be 8 times 2 minus x to the 3/2 over 3 plus c. The only real way I could kind of simplify that is if I factored out a negative 2, then I factored out a 2 minus x to the 3/2, because if I did that, then I'd be left with a 2 minus x squared over 7, then minus 4 times 2 minus x over 5, then plus a 4/3, still with a plus c. Not terribly simple, but it is just a little bit simpler in that this is kind of a nice descending order polynomial. You'd actually would want to multiply that a whole thing out and simplify it, so we won't do that right now. I'd probably just leave it like this. Okay, last one. The integral of x cubed root 4x squared minus 1 dx. So similar idea, I'm going to go u is equal to 4x squared minus 1, du is equal to 8x dx. If I know that x squared is equal to u plus 1 over 4, then I can start to kind of piece together what's happening with the x's here. So let's just kind of play this out. I'm going to do the integral. If I substitute, I get, let's see, I know that dx is equal to du over 8x, so I'm going to get a 1/8. One of the x's is going to cancel, giving me an x squared. Root u du. And since it's an x squared, I'm going to get 1/8 integral. X squared was u plus 1 over 4, so this is u plus 1 over 4. Root u du. Pull out the 1/4 and I get 1/32. And if I distribute the root u, I get u to the 3/2 plus u to the 1/2 du. And then I just go with what we did before. 1/32 integrated, I get 2u to the 5/2 over 5 plus 2u to the 3/2 over 3 plus a constant. I could pull the 2 out and get 1/16. I can leave it factored out, or I can multiply it in. It doesn't matter. But 1/16 u was to be 4x squared minus 1 to the 5/2 over 5 plus 4x squared minus 1 to the 3/2 over 3 plus a constant. I'll leave that there and kind of see if you guys can factor things out to reach would be a kind of an ultimate factored form of 4x squared minus 1 to the 3/2 times 6x squared plus 1 over 120 plus c. If you're curious, kind of take a look at that.